Welcome. My name is Carrie Donnelly, and I'm the director of the Chapel Hill Analytical and Nanofabrication Lab, or CHANNEL, at UNC. Today we will be talking about different types of optical spectroscopies and how they can be used to characterize materials. The colors that we see with our eyes are created by light interacting with matter in different ways. We see many different colors in nature, and people have been making brightly colored stained glass windows for centuries. Did you know that red stained glass often contains gold nanoparticles? And it is these nanoparticles that make it appear red. Let's take some time today to talk about how light interacts with matter on different size scales and how we can measure those interactions. When you shine light on a piece of glass, the light goes through the glass. We call this transmission, and we can measure the amount of light transmitted through a sample. When light is not transmitted, there are a few other things that can be happening. One is absorption of light. When you look at a red apple, the reason it looks red is because it absorbs all other colors of light, and the red light is reflected back to your eye. We can measure the amount of light absorbed and plot it as a function of wavelength, as shown here. The wavelengths are shown on the bottom of this graph, and there is an absorbance peak around 550 nanometers. Another way that light can interact with matter is for the incident light to reflect off the surface. This is what happens with a mirror, for example. Finally, light can also be scattered by a surface. Typically, this happens on rough surfaces, and the type of scattering will depend on the size of the particles doing the scattering. Now that we know something about how light interacts with matter, we can understand what we see with our eyes a bit better. The sun and the lamp in this picture both look bright because they emit light. The snow also looks bright, but this is because sunlight is reflected off the snow, and some of that light makes it back to our eyes. Lamp light reflects off the mirror. The couch looks red because it absorbs all other colors and reflects red light back to our eye. And the window transmits all visible light and allows us to see what's outside. But light interacts with nanoscale materials very differently. Bulk gold and nanoparticle gold look very different to our eyes. These vials all contain cadmium selenide nanoparticles. The only difference between the nanoparticles is their size. The nanoparticle size clearly affects the color of the solutions, and as the color of the solutions changes, so will the absorbance spectrum. Visible light has wavelengths between 400 and 700 nanometers. When visible light interacts with nanoparticles that are similar to or smaller than the wavelength of light, the light interacts with the material in a different way than it would with a larger bulk material. We now understand that the color of light absorbed by a nanoparticle will change as the nanoparticle's size changes. The way light scatters or reflects will also depend on the size of the particles. There are three different types of reflection and scattering: reflection in the ray optics limit, Rayleigh scattering, and Mie scattering. In the ray optics limit, the wavelength of light is much smaller than the particles. In the winter, snow can look especially bright because sunlight reflects off the rough snowflakes and reflects the sunlight back to our eyes. Rayleigh scattering happens when the wavelength of light is much larger than the particles that are scattering the light. One example of Rayleigh scattering is the blue sky. When light travels through the atmosphere, gas molecules in the atmosphere scatter the light. This process is wavelength dependent, with shorter wavelengths scattering much more than long wavelengths. More blue light is scattered and reaches our eyes than the red light, and therefore the sky looks blue. Finally, in Mie scattering, the particles are similar in size to the wavelength of light. In this case, the wavelength of light scattered will depend on the size of the particles. A cloud appears white because it contains small water droplets of all different sizes. Each individual water droplet will scatter a different wavelength of light, but the collection of droplets in the cloud will scatter all wavelengths, and the cloud will appear white. Here are the predicted absorbance and scattering spectra for gold nanoparticles in water, which show me scattering. The spectrum shape and peak position depend on what material the nanoparticles are made of and the size of the particles. Nanoparticles like these are used for quite a range of applications, from increasing light absorption in solar cells to enhancing chemical sensing. For all of these applications, we need to know the exact color of their absorption and scattering. For this, we turn to optical spectroscopy. For centuries, gold nanoparticles have been used to create red stained glass, and silver nanoparticles have been used to create yellow stained glass. At the time, the artists producing these windows knew that gold produced red colors and silver produced yellow colors, but they didn't understand that it was due to nanoparticles. If they did, they could have controlled the size of the nanoparticles to create other colors as well. The Lycurgus cup, a 4th century Roman glass cup, is another famous example of nanoparticle scattering and absorption. If the cup is lit from the front, the nanoparticles scatter green light, making the cup appear green. But if the cup is lit from behind, the nanoparticles absorb all light but red, and the cup appears to be red in color. It seems that the Romans also knew something about how light interacted with nanoparticles long before we did. In today's lecture, we talked about how light interacts with matter, and specifically how nanoparticles interact differently than large bulk materials. I hope you enjoyed this lesson on optical spectroscopy.